Okay, let's start our next section. And we're going to talk about optimizing Ruby code. どうぞ。
Thank you very much for coming again. Right. First, let me introduce myself. I'm Shyouhei. I'm one of our Ruby core committers since 28 or so. I remember. I was not an active developer for a few years, but I changed my job this February, so I can now develop new things like this one I'd like to share today. Let me briefly overview my BizTalk. I implemented what we call a Deoptimization on CRuby version 2.4. Under some benchmark I show you later, it boosts execution up to 400 times depending on benchmarks. Also, because this is a very fast attempt of this kind, it made lots of room for future optimization. Now, I know everyone has to say something about this topic, but Ruby is at least not the fastest language to execute in general. This is a screenshot of a site called Language Shootout, which compares various languages in their speeds. The chart shows the fastest language to the left and slower to the right. And it is obvious that Ruby is not the fastest one, and it's easier to count from the right. So there are many reasons explain why Ruby is slow, because like we have GC or we have GVL or Ruby being dynamic or something like that. But I'd like to say that it's all wrong. Ruby is slow because it is not optimized. This is an actual disassembly of how 1 plus 2 is evaluated. A bit noisy, but it shows the put object 1, put object 2, then send plus. It's doing that way. But wait, 1 plus 2 it is. It must be 3, right? The way we evaluate this is too complex. It should be just 3 like this. It's putting object 3. It should be like this. The reason behind why we can't do this is because I said 1 plus 2 must be 3 is wrong, in fact. It could be redefined dynamically and globally. So it is pretty difficult to say that 1 plus 2 is 3 beforehand. This is the reason why we calculate 1 plus 2 every time. That being said, redefinitions are rare. 1 plus 2 is arguably 3. People are not evil to break your first grade numbers. Of course, redefinitions are the part of Ruby language, so if it happens, it must work. But like I said, it's very rare, so it should not always be fast to execute. So I would like to introduce a mechanism called Deoptimization. Let's just forget about redefinitions for a while, because they won't happen. And only when they do, we then stop and throw away everything to fall back to naive execution. This is an overhead, in fact, so it makes redefinitions slower. But like I said, redefinitions are rare, so most of the time it works fast. Now, we are taking following approach to tackle. First, we do not compile the sequence into machine-native code or binaries. We don't introduce new binary format or a new way of execution. We optimize an instruction sequence to a more sophisticated one. In doing so, we are going to override the instructions on the fly. This means we cannot change the length of the sequence. Only modifications that preserves length are possible. In reality, we can fill non-operation instructions, so shrinking is kind of possible, but strictly speaking, we can't change length. Right, this diagram shows a part of Ruby internals. In Ruby process, VM execution, VM instructions are pointed from ISIC encoded field. VM instruction field of the RBISEC constant body, whose length is ISEC size. Apart from them, there are program counters somewhere outside abstract who points the sequence, which is typically inside of a machine stack. Now, in our implementation, two new fields named isec deoptimize and created are introduced to the RB isec constant body. The isec deoptimize is a simple copy of isec encoded. We'll visit the created field later. Now, all right. Assume we have some optimization. The blue ones are the optimization, and isec encoded got modified. How do we cancel this? It's easy. We save the sequence for this purpose, so just write them back. This is the actual deoptimization engine. Nothing is abbreviated. This is the whole. Of course, as you can see, the main procedure is the memcpy who is in the last two lines. The advantage of this approach is that first, it is expected to be highly portable because it is written in C. No JIT to native assembly is involved. Also, this deoptimization engine does not touch the program counters at all. This is particularly important because we don't have to bother any VM states. Because the only VM state that should be reverted is the sequence itself. Preparation is done only once. This also is an advantage when we encounter highly evil situations like tons of redefinitions continuing to happen again and again. Now, because we have to know when redefinitions happen, we are going to have a new state variable. This is the global VM timestamp, which is incremented when something happens, like constant assignments, method redefinitions, and module inclusion. This is the implementation. A bit long, so not everything is shown, but you can read that we introduced a new static variable called Ruby VM global timestamp equal 1, and atomically increment that in a function called RB next class serial. And there are other points that increment this variable, but it's very straightforward. We introduce a variable and increment it. And this is where the optimization is actually happening. The important part is the bottom half, which is a macro named call method. Strictly speaking, we do the optimization right after a method is called. This is because the increment of the state variable ultimately happens inside of this CC call function call. So when a call returns, there are chances something happened. We are testing that here. Another point where we do the optimization is VM push frame, which is a function that creates a function called stack frame. This one aims to purge an instruction sequence that were run hours ago and became stale at some point, then called back again. A huge advantage of this approach is it adds almost no overheads. The graph shows a preliminary experiment with all the overheads explained so far. It invokes methods many times, which should run the modified path. The graph shows it only slightly adds overheads, but as you can see, which is the overhead is in the margin of error, so it is very slightly. Okay, let's summarize what was shown here. We introduced the optimization engine onto Ruby. Its main characteristics include consistency of VM states, like the program counter. As a result, the engine works very lightweight. Now, we are ready. Let's have optimization, the fun part. Like I said, we refrain from touching VM states. We cannot change the length of the VM sequence, but under some such restriction, it is still possible to apply some kind of optimizations, like eliminating the method calls, folding constants, and the elimination of variables. Let's first see constant foldings. This is how a sequence changes before and after optimization in this format. You can see that there are several instructions before, which was transformed into one put object and a sequence of nubs. The nubs are meaningless, just to pad the instruction sequence to fill the blank area of the sequence, so that there are jump statements, and they should not be modified. So ideally, it changes the several instruction sequences into one put object. This is, in fact, pretty straightforward because constants are already inline cached. Back in one page again. Can you see the first deleted instruction is get inline cache? It is in fact inline cached. So we replace the set of sequence with already cached constant value. That's very, very easy. This is the implementation. The complex if condition, you don't have to understand this. This is checking the cache. If the cache hit, the if condition holds, and it goes into the block, then we additionally call the new function called isec constant for. This is its implementation. Very simple. It writes the buffer in with wipeout pattern variable, which is a series of nubs, then fills in the first two words. The wipeout pattern is a series of nubs. Then the first word is a put object, and the second word is the constant, which is well cached before. By applying the same modification, we can fold 1 plus 2. As you can see, the generated output is put object and nub, which is identical to the case of get constant. So it is just calling the same thing, and you can do the same thing. Next, send elimination. In this example, we call method n of receiver self, but we are immediately discarding the return value by adjust stack 1. This is a waste, so we squash them into a series of nub. That optimization, however, is not always possible. It depends on how a method is called and how that method behaves. So in this optimization, let us call a method pure if it's safe to be eliminated. The line is drawn like that. If it writes a variable other than local one, like global one or instance variables, then it's not a pure function. When it calls a block, it's not pure because the purity depends on the block. The block might have side effects, so the block calling method itself is not pure. Also, when the method is written in C, in this case also, that C function might be pure, but we cannot detect if the C function is pure or not. So we err on the side of caution, and everything written in C and categorized not pure. Lastly, when a method is calling another method, in this case, the entire call graph, everything that is called inside of method is pure, then it's pure. The calling method itself is pure. Note, however, that a method is either pure or not is too simplistic, because there are situations we can't say if it is pure or not. Suppose, for instance, when a method call results in method missing, in that case, we can't make sure if it's pure or not until we actually use that method. So in short, we have to detect a method purity on the fly. At the beginning, everything are marked as not predicted yet state. And as the execution progresses, some part of a method is detected pure or not. And finally, when everything fixed, the purity of the entire method is set up and then propagated to its callers. Let's say we know a method is in fact pure. Still, that's not enough. We have to check how the method is called. That is, if a method is return value is used, we can't eliminate because it is used. So we focus on the return value. If a method call is immediately followed by a pop instruction, then it means we can immediately discard because the return value is not used. This is where the elimination of send instruction happens. It happens inside of adjust stack, not the send. The diff is mostly common. It only adds one more function. The call function is this. Outside is very similar to the constant folding. It first squashes the sequence with the pattern here. Then if argh is non-zero, fills first two words inside of it. Well, the argh maneuver is somewhat complicated. If a method takes arguments, the argument might have their own side effects. So even when we can eliminate a method call, its arguments must be retained untouched. In this example, we are calling a method m with one argument, and that argument itself cannot be eliminated, but the function call can be eliminated. So after eliminating the function call, the argument is remain untouched, so we have to fix the stack not to be clobbered. Next, the variable assignments. In this case, we eliminate the assignments to local variable with value 2. The set local instruction is eliminated. Sad news is the implementation is not that simple. It 200 lines of long. So let me tell you briefly what is going on. It's not easy to tell if a variable is not used at all strictly. That must be called liveness analysis, and it's very heavy. Because we have to optimize on the fly, we need to do something lightweight. So this time, we check a variable if it is write-only or not. Also, there are bindings. So methods that are not pure might be subject to get binding and touch local variables from outside of it. We need to restrict the local variable elimination to pure ones. Lastly, local variables are shared across blocks. So blocks are checked recursively, not to oversee the usage of the local variable. Okay, let me summarize what was shown. Implemented several optimizations. For those people who measure compilers, it is obvious that what I did is very fundamental and simple ones. These optimizations run on the fly and preserves VM states. I have not mentioned about exceptions at all so far because it has nothing to do with it. The optimization explained so far does not interact with exceptions. Now, the benchmark. We tested what is proposed against 2.4 using Ruby's standard benchmark facility called make benchmark. The condition is shown, and I won't speak them out, but the situation I believe is somewhat normal. No new hardware, no new test suite, nothing special. And this is the entire set of results in one slide. This is how many times we made things faster. As you can see, there are cases we speed it up several hundred times. So that's very visible, but it's a bit difficult to take a closer look at other major benchmarks. So let's zoom things up. This is the same result in logarithmic scale, right? Same thing in log scale. The speed up ratio 1.0 means the speed up are even. Greater numbers shows the our strategy is beating a trunk. The smaller, the slower. From what we see, almost all benchmarks are slightly slower than the original. And among them, few benchmarks achieve extraordinarily fast result. Let's look in detail. The results shown are those benchmarks got faster. And beware that it's execution time, not speed up ratio. if you look at it, you find there are several set of benchmarks that speed up to similar execution times like them. They are because they are optimized to generate identical instruction sequences. So the benchmark aimed to look at different things, but because optimization did result in same thing, they have the same result. And at the same time, there are cases where we slowed down. Out of these benchmarks, what is interesting is the VM2 eval, which has tons of what I said eval activities. This example shows the overhead of optimization, deoptimization, and I think it's meaning marginal, because eval can be much slower in other kind of deoptimization engine. Other things that got slowed down, notably the block-related benchmarks got slower than the original. They are because we have to recursively scan the blocks in order to detect the local variable usage. However, variable elimination is in fact powerful because not only the assignment itself, but also the entire allocation of the object can be skipped. So it impacts very much when they work. The fastest example in the benchmark were those variable elimination got effect. For instance, this VM1 GC, which is the first one, got faster not because we modified GC, but because we skipped allocations. Again, this is the entire benchmark result. You can see that it's very slightly slowed down when they slow down, but when they slow up, speed up, when they speed up, this drastically speed up. All right, let's have a conclusion. I implemented what we call deoptimization on Untitled Ruby version 2.4. Under some benchmark I showed you, it boosts execution up to 400 times depending on the benchmark. Also, because this is a very fast attempt of the kind, it made a lot of rooms for future optimization. Let me tell you about the future optimization briefly. Sub-expression elimination is possible because that should reduce the size of sequence, not grow. So it works our strategy. More strict library analysis and escape analysis should make things more fast also. If you choose to allow modification of VM states, such as program counters, exception tables, these things also makes other rooms for optimizations. All right, that's all. Thank you very much. But one thing, I tested this using Rails. I tried running Rails on this very laptop, and got this result. It seems only has overhead, and no optimization was in effect. The hours got slower. A good news is that, however, it seems no memory overhead is there. So as far as we don't optimize, there is no overhead. So so that as far as we see Rails, we still have a lot of things to be done to actually get your application faster. That is all. Thank you.